This video starts the discussion on Part C of Topic 4. In Part C, we will discuss the extension of LL1 grammar. These are grammars that have additional capabilities, and they are translation grammar, attributed grammar, and attributed translation grammar. In this video specifically, we will discuss translation grammar. Let's start. All grammars and programs that we have developed previously are capable of checking syntax. We can check if a particular input string or expressions are accepted or rejected by a particular grammar. However, we didn't look at the semantic of input string. So what exactly are semantic? Semantic is the intent or meaning of our source program. So for example, if we are parsing a sentence in Malay, saya suka makan. So we know that these three words, saya, suka, and makan, they are words in Malay. Therefore, the syntax of the sentence is correct. But what is the meaning of this sentence? We must be able to parse I like to eat from this sentence, because this is the meaning of the sentence, and this is what we mean by semantic. To determine an intent of a particular input string, we now will be introducing action symbols. So action symbols gives the capability of producing output or calling other methods while parsing an input string. And action symbols in grammar is enclosed in curly braces. Translation grammar is grammar that contains action symbols. Grammar 17 is an example of translation grammar. And if you notice in grammar 17, we'll be able to see action symbols, which are symbols enclosed in curly braces. So rule number 2, rule number 5, and rule number 8 have action symbols. This grammar 17 is a grammar that is capable of translating infix expression involving addition and multiplication to postfix form. So why do we need to translate infix expression, expression that has operators in the middle of operands, to postfixed? This is because postfix and prefix operations are more easily parsed by computers. Meanwhile, infixed are used by humans. When we talk about grammar, we have discussed three different types of grammars previously. We talk about simple, quasi-simple, and also LL1. For all these three types of grammar, we need to find the selection sets before we can do operations on them. This is similar to translation grammar, since translation grammar is actually an extension of LL1 grammar. Therefore, we need to find the selection sets for translation grammar. However, there is one difference. We can use the 12 steps in order to find the selection set, but before we do that, all the action symbols need to be moved out first. So if you look at grammar 17, we have noticed before that grammar 2, grammar 5, and grammar 8 have action symbols. So once we take them out, we are left with the underlying grammar. And this is the translation grammar with the action symbols removed. And once we take out all these action symbols from the grammar, we are left with grammar 16. And grammar 16 is grammar 17 with their action symbols removed, because if you look at grammar rule number 2, rule number 5, and rule number 8. Grammar 16 is the same grammar, just with the action symbols removed. And underlying grammar of grammar 17 is grammar 16, and this is the same grammar that we have discussed previously, and we have used the 12 steps to find the selection set for grammar 16, and this is the selection set for grammar 16, which is also the selection set for grammar 17. In order to demonstrate the capability of translation grammar to produce output, we will draw a derivation tree. So we're going to use grammar 17 to draw the derivation tree for this particular expression. So this is our input. So just like what we have learned previously, we're going to start with the starting non-terminal, and the starting non-terminal is expression, and there is only one rule derived from expression. Therefore, I'm going to start with the first rule. Expression can be derived to term elist. We are currently trying to write var, and need to write it under term. So there is only one rule derived from term, which is rule number 4. So I'm going to directly apply rule number 4. Term can be derived to factor tlist. And there are two rules derived from factor. Since we are trying to write var, I'm going to choose the rule derived from factor that has var as parts of its selection set, and that rule is rule number 8, because rule number 8 has var as its selection set. Therefore, I am applying rule number 8 here, and if you can pay attention, this is how we're going to do this. Var, and then write the var action. Okay, so we are done with the first var. The next input is plus, and we need to write it under tlist. So there are two rules derived from tlist. We need to choose the one that has plus as part of its selection set, and that rule is rule number 6. Okay, so I'm going to apply rule number 6 here, and oops, okay, so rule number 6 is still is derived to epsilon, which means we still haven't write plus inside our derivation tree. So we move up to elist, and we need to choose the rule that has plus under the selection set, because we have two rules derived from non-terminal elist. So we choose rule number 2, because rule number 2 has plus as its selection set. So I am applying rule number 2 here, plus term, and then we have an action symbol. This is plus action, and elist. Okay, so this is done. Next, we move to var, and we write it under terms, and since there is only one rule derived for term from the non-terminal term, so I'm just going to directly write rule number 4, term derived to factor and tlist. And then again, I will be applying rule number 8 here, because we are writing var. Okay, so this is done. Next, we want to write times under tlist. Since we have two rules derived from tlist, I will choose rule number 5. since rule number 5 has times in its selection set. So this will be times factor, then we have times action, an action symbol, and finally we have t-list. So we are done with times, and finally we have var, and we need to write it under factor. So again, this will be an implementation of rule number 8. Okay, so we are done with the input string, but since we cannot leave these non-terminals hanging, so we just apply epsilon to them. Okay, so this is an implementation of rule 6 for this one here, and this is an implementation of rule 3. Okay, next what we should do is we should take out all the leaves, and we read it from left to right. So it means we need to take out all these leaves. Okay, plus var action times var action times action plus action. So as the output, it's going to be var action, and then we made plus first, plus var action times var action times action plus action. And finally, we will just take out or isolate all the action symbols only. Therefore, we're going to get this is the final output, var times plus. Therefore, for this input, var plus var times var, this is the output. var times plus. From this infixed, we get this postfixed. Just like LL1 grammar, we can construct an extended pushdown translator for our translation grammar. The rules are basically the same, just that each action symbol will have its own rows in the pushdown machine. So this is what I'm talking about. And fill up every column in that row with alt A, which A is our action symbol, pop, retain. And action symbols will be treated as stack symbol. They can be pushed onto the stack exactly the same way as terminals and non-terminals occurring on the right side of a grammar rules. So this is an extended pushdown translator for our translation grammar. So let's go through one by one. So grammar 17, we have 8 rules. So let's take a look at rule 1. So rule 1, the selection set is left parenthesis and var. So expression that intersect with left parenthesis and also var, we fill it up with replaced, elise, term, retain. So this is basically the same method of constructing pushdown machine for LL1 grammar. So for all the other rules, you will see exactly the same thing. So now let's take a look at rule that has action symbols. So this is a rule that has action symbol. Rule number 2, the selection set for rule 2 is plus. Therefore, where elist intersect with plus, we fill it up with replace elist plus action term plus retain. So it is just basically the same thing that we do. Okay, now each action symbols inside our grammar. So how many action symbols do we have? So we have plus, multiply, and var. So we have 3 action symbols. We have var action, plus action, and times action. Each of these action symbols will have their own rows. So this is the rows for var action. This is the row for plus action. And this is the row for times action. So inside the cells for each of the rows here, it is filled up with only one thing. Pop retain out the action symbol itself. Therefore here, because this is the row for var action, it is filled up with pop retain out var. And this is because this is the row for plus action, it is filled up with pop retain out plus. And here, because this is filled up, this is the row for times action, it is filled up with pop retain out times. So this is the only different thing with regards with push-down machine construction for translation grammar. The rest is exactly the same with the LL1 grammar. So you can see here with terminal that meet with itself, pop advance, pop advance, pop advance, pop advance, pop advance. For nullable rule, we have pop retain. Bottom marker that meets with end marker, we have accept. As the rest of the empty cells, these are all rejects. Now, how do we write the methods for the recursive descent parser for our translation grammar? It is also exactly the same steps that we take when we write the methods for recursive descent parser for LL1 grammar, with just a few modifications. So we need to look at rules that have action symbols. So in grammar 17, again, the rules are rule 2, rule 5, and rule 8. And these 3 rules are derived from 3 non-terminals: non-terminal elist, non-terminal tlist, and non-terminal factor. So these are the 3 methods that we are interested in. Okay, so this is the method for non-terminal expression, which is exactly the same as like in LL1 grammar. Now let's take a look at the next method. This is method elist, and just like we have established in the previous slide, we have an action symbol for this rule 2, which is derived from non-terminal elist. So let's take a look at how do we write the recursive descent parser for method elist, especially when applying rule number 2. Okay, so first we check if the current input is our selection set. So the selection set for rule 2 is plus. If input equals to plus, and then after the derivation arrow, we meet a terminal. So we handle terminal by calling the next input. So we write this line, input equals to get input. And then we meet a non-terminal term. So we handle a non-terminal by calling the method for that non-terminal. So we call the term method. And then we meet an action symbol. So this is where it is different. We handle action symbols by printing out that symbol. So we write system.out.print plus, because in this role we have plus action. Next, we meet a non-terminal elist and we call out the method for non-terminal ELIS, and that's the end of rule 2. As for rule 3, the method is the same as in the previous LL1 grammar. Now let's take a look at the next method. Term method does not have an action symbol inside the rule number 4, so we're going to skip this very quickly. And the next method is Tillis method. So Tillis method or Tillis non-terminal is derived for the rules 5 and rule 6. And rule number 5 has an action symbol inside of it. And just like in previous ELIS method, we handle this particular action symbol by printing the symbol out. System.out.print multiply. Okay. And then the next method is factor method. For factor, we have rule 8 that has an action symbol. And again, we address this by printing out var, system.out.print var. And this is how you write the recursive descent parser for translation grammar. We handle action symbols by printing it out, system.out.print. And I hope that clarifies how to construct a translation push-down machine and also to write the recursive descent parser for translation grammar.